Okay, we have a situation, we have 500 sane people, 500 demented people. 10% of your sane become demented, 20% of your demented become sane. How many of each are there going to be? Well, we very quickly got that. You got 5, and this is why I illustrate it, that's, you know, but you can see it kind of clearly here. 10% of 500 is 50, 20% of 500 is 100. So you're going to have 50 of these guys going over here, 100 of these guys coming over here. And you're going to end up with 550, 450. Then you can do it again and again. Okay? Now, if you do it twice, you see you got a gain of 50 and a gain of 35, and you say, is there a pattern to these numbers? Well, it's a little early to establish a pattern. Reasonable to say, well, that went down by 15, should go down by 15 again. Okay? Now, if you got deep mathematical intuition, you probably would say, nah, it can't be that simple. Maybe it's exponential. Okay? And of course, you should understand the connection with an exponential function, but maybe not. But the point is then, with every sequence, if it is exponential, you would have the same percent change. It's a property of exponential functions, which you get more of when you're in calculus. You can prove it in calculus. You can actually prove it in pre-calculus, but we didn't do that. Had enough to do. Okay? So this is 70% of this. So this is 70% of this. There it is. We speculated on this before we calculated it, but then we did the calculation, and yeah, that's what came out. Okay? And it's going to continue. All right? Why is that? Well, linear algebra provides a really elegant way to see why it is. So I'm going to kind of outline it for you. Okay, but there's the pattern. Now, I can draw a picture. Okay? This is going to be your number of sane. This is going to be your number of demented. And I'm going to draw some arrows. It's going to come out here to 500. It's going to come over here to 500. And I'm going to draw an arrow from this point, from the origin out to this point. Okay? And that arrow I'm going to call a vector. With braces or brackets, 500, 500. Okay? There are many notations for vectors. Ordered pair, 500, comma 500 with an arrow over it. That also represents a vector. And ordered pairs, ordered n tuples, and we'll see that later. Okay? Actually, we'll see it pretty soon. Okay, so anyhow, so you got this vector, 500, 500. And then we have the 550, 450. Well, 500 is there. Let's see, 1,000 would be about here. So we could divide that about here, 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 and here. So there'd be about 600, 550 would be about here, and 450. Maybe here. So I'm going to say that's your 550, 450. That would be this one. Okay? Then we have our 585, 415. So 585, 415, maybe there. Okay? It's not going to be a very accurate picture. There's something I could have done to make it accurate, but then I'd give away something else. Okay. And then you got your 609.5, 390.5. That might be here. These vectors are getting closer and closer together, kind of bunching up. okay? And of course, the reason is they're changing by less and less. So the question is, well, what do you know about a geometric sequence? Does it converge? You ought to know.
I wouldn't think so in general terms.
I'm sorry?
I wouldn't think so.
Well, it does. Okay? And it's a fairly standard thing. So you kind of want to maybe become aware of it. Although it's not going to be necessarily that relevant to the course, but the geometric sequence converges. Okay, so I can write this down. I'm trying to decide how much to write. I'm going to go ahead and write the formula. (50 times 0.7 raised to the n). So if n is 0, you get 50. If n is 1, you get 50 times 0.7. That's your 35. If n is 2, you get 7/10 of that. That's your 24.5, and so forth. Okay? Add them all up. Sum approaches 50 times 1 over 1 minus 0.7. That's just an incidental fact about geometric sequences. But the other fact is, every time you multiply by 0.7, this number gets smaller. So clearly, it's going to get 70% of its former value. You keep doing that, well, just like if I'm walking to that table, if I go halfway, then halfway again, and keep doing that, I never get to the table, but the table is my limiting position. Well, the same is true if I go 30% of the way, which puts me at 70% of the former distance, right? Then 30% of that, and 30% of that, and so forth, okay? We're still going to approach the table. It might take me a little longer to get within a given distance if I start from the same place. Okay, well, that's kind of an important idea, because this tells you that these vectors are ultimately going to stop. They're going to approach some limit, okay? Because what you're doing is you're going 70% closer to something, and then 70% of, well, you're going some distance here, then 70% of that, 70% of that, 70% of that. It's going to stop somewhere. So we have what we call a limiting value. Actually, I'm going to draw it like this. And the limiting vector is what occurs when you have no change. Now, just intuitively, with your arithmetic, can you speculate on what these two numbers would have to be, or how they'd have to be related in order to get no change? What could you say about the two numbers? You might not give me the exact numbers, although Wouldn't be too hard to do that.
One of them would literally have to be twice as large as
Exactly.
the other.
You have to have twice as many sane as you have demented.
Sane and demented would just switch out at that point.
Huh?
Sane and demented would just switch out at that point.
I'm sorry, I can't hear you over Sarah.
Sorry.
And she's 100 miles away.
Sane and demented would just switch out at that point.
Yeah. Yeah. If this number's twice as big as this, then 10% of this equals 20% of that. You could set that up as an algebraic equation. Okay, you could say, okay, 0.1s equals 0.2d, so s equals 2d, right? Okay. Also, you're just swapping individuals, so s plus d has to be 1,000, right? So you can figure out what the numbers are very easily. It's 1/3 of 1,000, 2/3 of 1,000. Okay? 333.3 repeating, 666.6 repeating. Okay? So we can easily figure out what this limiting vector is.
So it'd be like 333.3 repeating for sane people.
Yeah, 666 repeating for sane, 333 repeating for demented.
Oh yeah.
Okay?
Not bad.
So these vectors geometrically approach this vector, always moving 70% closer. The tip will always move 70% closer, okay? The point at the end of the vector. Make sense? Okay. These points lie in a straight line. I drew them kind of like they might lie in a straight line, but do they? Should they? I'm sorry?
No.
Okay, no? Because most things don't lie in a straight line, it'd be your first expectation, wouldn't it? Okay? Anybody see a reason why they might lie in a straight line?
What's lying on a straight line? Are we talking about the vector line?
Talking about the points at the tips of the vector, do they lie in a straight line?
No.
But, you know, if you look at my picture, they probably don't.
Scale.
Huh?
Scale.
But if x plus y equals 1,000, what's that
The
the
1,000
equation
is the
of?
limit, yeah.
Straight line of slope
Yeah.
-1 with intercepts of 0, 1,000 and 1,000, 0. Right? So s plus d equals 1,000, just like x plus y equals 1,000. You have a straight line from 1,000 up here to 1,000 down here. Now, it doesn't agree with the way I scaled it because the way I drew these. I said, you know, I could have drawn the straight line and then put all these on the line to make a more accurate picture, but I would have given away the fact that it's a straight line that I wanted to kind of remind you of and think about, because straight lines are real important in linear algebra. Linear. Straight lines, planes, flat hyperplanes, whatever that means. Okay? And I can tell you what it means, but you haven't had multivariable calculus. So. Okay? Make sense? Okay. Well, quite a lot of content right there. We haven't proven any of it. We've established a pattern here. We haven't proven the pattern, have we? It looks pretty convincing. You know, just this much makes it look pretty convincing, and I've asserted that it's so, and it is, but I haven't proven it. So you ought to be a little bit skeptical and ask yourself, how would I prove that? Well, there are many ways to prove it. But linear algebra gives you a really neat picture. So I want to go on now and give you a calculation skill. A little more sophisticated than this one. So I'm not sure I want to write that down yet. I don't want it right there. Don't want it just yet. Okay. So you have S and you have D. Some number sane, some number demented. Okay? Some of the sane become demented, the rest of the sane stay sane. Okay? And some number of demented become sane, some number of demented stay demented. So we know that 0.1 times S of the sane become demented, right? And point 2 D of the demented becomes sane. Who else is going to be sane? Well, point 9S remains sane because 10% of them become demented. 0.9, 90% of them are going to stay sane, right? And we can say that, and that almost looks like a 0.95. Let me get that as a little curlier. Point 8 of your demented becomes sane. Okay? I would write a little more elegantly with SD here. Okay, and then we have SD in the next step. Okay? So we have 0.9 S here, and we have 0.2 D. And then we have our 0.8 D and our 0.1 S. Your diagram kind of like that. We could cross the arrows too, but it's easier to label if we don't cross them. So we get the picture. Okay? Now I'm going to introduce a very simple convention. Got a row vector and a column vector. And when we have a row vector and a column vector, we can multiply them. And it just means we multiply whatever's in the first number in the row by whatever's the first number in the column, and the second number in the row by the second number in the column, and we add them. Okay? Okay? So tell me. Fill in the blanks.